All right. Okay, good. It can hear me this time. So, uh, I shut the webcam overlay off so you guys won't be able to see my face if you go back and watch this later. Um, Not that any of you would want to see it anyways, but uh, my name is Bradley. Uh, I was a member of 2648 for 4 years, 2009 to 2013. Um, During that time, I was webmaster and one of the programmers on the team later during my time. Um, and now I spend time helping the Lawrence team with electronics and programming. And one thing that was brought up when I was at Spirit was for us to do sort of something like this, where I come and talk a little bit about electronics and programming. Tonight is going to be all about electronics. If we finish early, then we can either ask questions or we can look at some of the stuff that I've done. Um, but I think that I've got enough stuff to talk about that we will be able to uh, get through it without having too much issue in terms of length of content. Now, one thing that I do want to say is that this is a very, not generic, but a very light introduction to electronics and programming. Um, my end goal is that you guys don't go to work on the robot and plug something in backwards. You know how to identify things on the robot and what they do, at least generally speaking. And if you notice something that looks strange, you at the very least know how to dictate to someone else what you think looks strange so that you both can assess it before you try to turn the robot on. So one thing that I always like to start with that I don't have any pictures for. I had a PowerPoint all made up and it's disappeared. I reimaged a computer the other day. I have a feeling that that's where it was and it wasn't in my Dropbox, which is a problem. But I'll deal with my own stupidity later. Um, One thing that I want to talk about is voltage, current, and resistance before we start in on anything specific to the robot. Now, there's a lot of stuff to those three things that we could talk about. I just want to talk about them really, really quickly um, because they do come into play with robotics. A lot of the stuff that you will do with them is thought out for you, so to speak. If you were designing an electrical system from scratch, you would deal with these a lot more and specking out what parts you need and how much power will be running from one location to the other. But First does a really good job of providing you with hardware that makes it so that you don't have to deal with that aspect of it. But to start in, let's talk about voltage a little bit. Um, you all probably have a very general idea of what voltage is, I'm guessing by this point. You probably know that there's 120 volts roughly coming out of the wall outlets in your house. Car batteries are 12 volts roughly, stuff like that. Uh, Normally when I talk about stuff like this, I relate it back to something called the electronics water model, which tries to map electronics to a water system. It is not perfect, but it does work fairly well for explaining voltage, current, and resistance. Voltage would be like the pressure on a water system. How much force is behind the water that is moving through a pipe? Can anybody tell me what happens when you push too much water too quickly through a pipe? You usually break a seal and it goes bang. That's basically what happens. Um, so there's a very similar scenario with voltage. You push too much voltage through a circuit, it won't go bang, but it's going to start to smell really bad and it's going to get hot very, very quickly. Um, as I said, First does a really good job of protecting you against this. Granted, these protections are not perfect, but most of what you will do with an FRC robot is either with 12 volts or 5 volts. There's a little bit of 3.3 volts mixed in there, but that's only as you start getting into dealing with sensors and stuff that doesn't require as much pressure in order to get it to function. Current is the counterpart of voltage. You can sort of think of current as the volume of water. Current is the actual energy that is available to be used by the robot for a particular part of the circuit. Having too much current, provided that you actually have a circuit in the way, is usually not a big deal. A component will only pull as much current as it actually needs to function. So, for example, this laptop pulls 45-watt charger, like 2.5 amps while it's charging, and it won't pull any more than that. If you plugged a charger in that had a greater amperage output on it, it's not going to try to suck in all that extra current. Current becomes problematic when you try to pull too much current through a circuit. That can also generate an exceptional amount of heat and make things smoke and melt and cause problems. One horror story, I can see Pete laughing. One story that I like to tell is in my senior year on Infinite Loop, my friend Brady was trying to fix the battery terminals on one of our batteries. And he had a screwdriver about that long. I was about 30 feet away from Brady with my back turned to him. And all of a sudden, I see this great big blue flash. And I turn around, and Brady is probably 3 or 4 feet back from the battery that he was working on. And he's holding up the screwdriver, and I can see that a chunk of it is missing. He had apparently shorted the poles of the battery across the metal part of the screwdriver, and all of the current from the battery sumped into the screwdriver and then back out again, and had managed to burn off a piece of the screwdriver. You wouldn't think metal could burn, but it can, apparently. So, while most of what you will do on an FRC robot is exceptionally safe, there are safeguards in place to protect you in the event of an accident. Not all of them are perfect. You still have to take precautions when dealing with anything that has to do with electricity. I'm not going to tell you that anything is explicitly safe. Even the smallest voltage at the smallest amperage. Always take great care when dealing with something in electronics. That being said, the last piece that I want to talk about real quick is resistance. You can think of resistance sort of like a kink in a pipe, like going from a 1-inch pipe to a 1/2-inch pipe and then back to a 1-inch pipe in a very short span of space. Depending on how you configure what is creating the resistance, you can resist voltage or current, depends on what you're doing, and there are equations that explain why this works and the way it works, but we won't deal with that. Resistance is not something that you deal with much in FRC unless you get down into the nitty-gritty of the math, like how motors function and what happens when a motor stalls and stuff like that. There are certain sensors that use resistance, one of the most common being a potentiometer, similar to an analog dial on a radio. But that is beyond the scope of what I want to talk about tonight. We may touch on it very, very quickly, but resistance is one of those things where, yes, it is there, and yes, it is a component of it, and I want you guys to know it. That way, if you hear the term, you know what to look for more stuff. But it's not necessarily something that you will deal with on a regular basis if you're just plugging wires in. current and voltage is, though. You plug wires into the wrong voltage and something's either going to blow up or just not work. You plug something into the wrong current and it probably just won't work. Probably because you didn't source enough current to actually make it work. The last thing that I want to talk about on this real quick part is protecting your electronics. I struggled with making people do this when I was on 2648. I struggled with people on 6172 with this. If you are drilling, cutting, doing something that is going to fling metal shavings, plastic shavings, something like that, all over your robot, cover your electronics. About, what was it, a month ago? I was handed one of our RoboRios, and it had something called a short fault. It means that somewhere on the device there was a short from a positive lead directly to ground, no circuit in the way. The RoboRio's smart. It protected itself and shut that channel off, but the RoboRio wouldn't function until I could find where the problem was. So I took it, and I took the back of it off, and took the PCB out, the printed circuit board that actually makes up the RoboRio's internals. And I tapped it on my bag. I had my bag open, wherever my bag went. Tapped it on my bag on the workbench. Metal shavings everywhere. I'm like, oh my god. So, needless to say, that RoboRio still does not work. I cannot find for the life of me where the short is. It could be a permanent short. It could have burned into the board. It could have shorted across two contacts and soldered the metal shaving that's in there somewhere to two contacts, and the RoboRio is just constantly protecting itself because it doesn't know what else to do. But right now, that RoboRio can't be used for competition because somewhere there is an eyelash-sized piece of metal across two pins, and I can't find it. So, cover your electronics with drilling or cutting, even if it's just plastic. You don't really want anything getting in there. Metal is the worst, but plastic isn't that much better. Keep your stuff safe. I mean, a RoboRio for a robotics team is $435. A PDP, a power distribution panel, $200. And it doesn't get better from there. So keep the expensive stuff safe. The other thing I like to mention is if you're working on the robot for whatever reason, whether you're drilling, cutting, pulling wires, adding wires, shut your robot off. We had an incident a couple of years ago where one of Lawrence's students, I don't know if you guys know what a PWM cable is yet. It's the 3-wire cable that has a black, a red, and a white wire that's normally used to drive motors and connect sensors like encoders. Well, inside those wires is stranded copper. It's stranded so that it's nice and flexible and easy to use. Somehow, one of our students managed to fuse it into solid core while it was plugged into the RoboRio, which is bad. Granted, it didn't damage the RoboRio, luckily enough. I tested the RoboRio afterwards and made sure it was fine. But it is a testament to shutting off your robot if you are working on it, regardless of what you're doing. The last thing is something called total load and what happens when a breaker pops. On your PDP, you have breakers, 20, 30, and 40 amp breakers, and you have a main breaker, which is rated for a lot more, 120 amps of constant load. Not talking about burst load, but you may find that if you are putting an extreme amount of load on either a 20, 30, or 40 amp breaker, it will pop. And in extremely rare circumstances, you may pop the main breaker. Basically, what a breaker does is what the name implies. It breaks a circuit because you are trying to pull too much energy through the circuit. And it's trying to protect you from melting something. you are required to put a breaker into each channel on the PDP that you're using. So if you got a motor plugged into it, something else, you've got to have a breaker in there that's rated for what it's going to be using. Most of the bigger motors like Sims, the big black ones that are normally on drivetrains, those use 40s. Smaller motors like window motors, Fisher-Price motors, Bainbot 775s, those use 20 and 30s. Normally, in most circumstances, you will never pop a breaker. We propped our main breaker a couple of times last year because our gearbox was built in such a way that it created a huge amount of resistance inside the gearbox itself, and we had three big motors on each gearbox, so for a total of 6 Sims on our drivetrain. And from what I could tell from the math that I did, we were dragging the roughly maximum load that the battery can put out in burst, which is 600 amps, which would be enough to melt a person. So, yeah. So, it is very, very rare that you would pop the main breaker, and it is rare that you would pop a 40, a 30, or a 20. Normally, if you're going to pop one of them, it's because you put a motor that wasn't designed to be on that particular type of breaker on that breaker. It varies with what you're doing, and there are circumstances that can change that condition, but more often than not, that would be why. You put too big of a motor on a particular breaker, and it stalled out. It stopped moving even though it was having power applied to it, and it just... Now, granted, the ones that go on the PDP are self-resetting. You take the load off them for 10 seconds, and you'll hear a click, and they'll be back to functioning. The main breaker does not do that. The main breaker is designed to cut power to your robot if there is a problem. If the main breaker is popping, that means there's a problem. So that one will not self-reset. But all the ones on the PDP, if you do overload them, you'll hear a snap, and they're actually called snap action breakers. You'll hear a snap, and they'll come back alive, and the channel will start working again. So that being said, let's talk a little bit more specifically about robot stuff. I assume you've all probably seen something like this before. This is the RoboRio. This is the brain of an FRC robot. One thing that I always like talking about is, and I actually talked to Keith a little bit about this at Spirit, because this is always fun. The RoboRio is not an exceptionally powerful device. Its processing power to your average everyday device is almost a joke in how slow it is. Your average modern cell phone is multiples upon multiples upon multiples faster than what a RoboRio is. But a RoboRio has been specifically engineered to meet a certain task, whereas your phone has been designed to meet a wide variety of tasks in a very sort of kludgy way, just sort of having enough stuff to do generally everything as opposed to a specific set of things. That being said, just a general idea for those of you who know a little bit about computers. RoboRio has a dual-core processor, ARM-based. It runs at 667 megahertz. Your average laptop nowadays that you go and buy in the store is usually 4 cores and runs anywhere between 2.4 and 3 gigahertz on the high end if you're buying an average one. For RAM, it has 256 megabytes of RAM. The laptop on my left has 8. The laptop on my right also has 8. I haven't upgraded my work laptop yet. And it has 512 megabytes of program storage. That's it. Basically an oversized Arduino, yes, for those of you who know what that is. So it's very, very, not underpowered, but very, very, designed very, very specifically for what it has to do. For what you're doing, you really shouldn't be pushing it beyond 256 mega RAM. If you're maxing out the processor, what are you doing? Why are you doing it? Is there a better way you could be doing it? There are some teams that do offload certain things to other devices by attaching them to the robot's network. But for the most part, like 99% of teams can get away with just using the RoboRio and whatever they're using for a driver station to get the work done that they need to. Now that being said, the RoboRio does have a little bit of help. And it does have, and this thing that it has helping it is not something that is exceptionally common in modern computers, although it's not rare either. The RoboRio has something called an FPGA. It stands for a Field Programmable Gate Array. It is basically programmable hardware. This is not something that you will probably ever have to interface with unless you are doing something exceptionally complicated. Because normally what happens is when you do a firmware update on the RoboRio, when you install a new operating system on it, the FPGA is updated automatically for what it needs to be able to do. The FPGA handles a lot of grunt-worky type stuff. It handles things like reading a voltage and timing, making sure that the robot can keep accurate times so that it gets packets from the driver station at the appropriate times. It helps to facilitate the onboard electronics protections, like the short file protection that I was talking about earlier. It helps trigger the cutoffs that stop power from running if there is a problem. It does a lot of the work that would really cause any other modern processor to drag. And while there are ways, don't laugh at me, Pete. While there are ways that you can interface with it and use the extra space that it has on it to do stuff, I have never heard of a team doing that, because it does require a specific programming language to do it. You have to use LabVIEW. I generally have not seen or heard of any team actually doing that.
Actually, in China they use LabVIEW. So.
Well, yes, LabVIEW is used, but you don't necessarily have to use the FPGA if you're using LabVIEW.
Yeah.
I've written robot code in LabVIEW before. It's not fun, but I've done it. So now, just as a quick rundown, you guys can see all along the sides of the RoboRio here that there's all kinds of stuff. I just want to talk about each one really, really quickly. You guys can sort of see my mouse moving around. Over here is PWM. PWM stands for pulse width modulation. Basically, what it is you're turning a signal on and off really, really fast. I'm talking like nanosecond or microsecond time. PWM is normally used to control motor controllers. At least that's what it's classically used for FRC robotics. There are other uses for it, but for the most part, if you see a team using PWM, they are using it for driving their motor controllers. Over here on the opposite side, with the same rail length, is digital I/O, or DIO. Stands for digital input and output. This is how you would take in on and off signals from like a sensor. Most common use for this is limit switches, like the light switches in your house, except usually with bumpers and not actual switches. Digital I/O is also used for ultrasonic sensors, sending out a ping and waiting to hear it come back. And it's also used for encoders, things that measure distance traveled and speed of travel. Analog I/O is a little bit all over the place. Analog I/O obviously standing for analog in and out. Analog in is down here, and the only analog output is on this thing right here, which we'll talk about in a minute. To speak to analog in takes in a continuous voltage. It can vary. It doesn't have to be on or off. It can be some value. In this case, a lot of what teams will use for analog in is with potentiometers, like if they have an arm or something that they want to know the angle of at any given time. 2648 tried to use a couple of potentiometers in our 2011 season. One thing that I will say is, just to speak specifically to potentiometers for a second, make sure you know how far a potentiometer can turn before you try to use it. If you overturn a potentiometer, it doesn't get hot, it doesn't smoke, it just explodes. It breaks right in half. I mean, just poof. We broke probably 4 or 5 potentiometers in 2011 trying to get our arm to a setup where we could actually measure what angle it was at, and it never ended up working because we kept breaking them, and we ran out of time. Next, I'm going to talk about a couple of communication types. I'm going to talk about them in order of importance. At least importance in the context of what I've seen you guys use in the past. The first one that I want to talk about is CAN. CAN stands for Controller Area Network. Nowadays, CAN is normally used in cars. CAN is actually, if your parents have ever complained about their engine light being on, that's CAN. The computer in your car spoke to a sensor. The sensor said that there was something wrong, and the computer told your dash to turn the engine light on. CAN is what I call a shouty form of communication. You can think of it as everybody being in the same room, and everybody has a number. When somebody wants to send a message to somebody else, they hold up their number, and they shout the other person's number as loud as they can. When the other person hears it, they hold up their number, and then they talk back and forth, and no one else is allowed to talk until both people put down their numbers. It's the best way to describe it. If 2 people hold up their number at the same time and start shouting, the person with the lowest number gets to talk first. That's CAN in a nutshell. It's a little bit more complicated when you have 20 devices on a CAN network and all of them have 30 different IDs that they can respond to, 30 different numbers that they can respond to. But in a very short example form, it's basically a bunch of people shouting in a room. CAN nowadays for FRC robotics is normally used for controlling motor controllers without having all kinds of PWM wires running everywhere. Because CAN is bust, You don't have to have wires running from one device to the next for each device. You can just sort of chain them together. So that way you have the same 2 wires running to all of your devices without having to have any extra middleman connections to the RoboRio. There's only 2 wires running to the RoboRio for everything. The other thing that CAN is used for on the robot is it is used for communicating with the power distribution panel, which we'll talk about in a minute, and something called the pneumatics control module, PCM, which is another thing that we'll talk about very quickly. Next communication type is SPI. It stands for the Serial Peripheral Interface. A little bit more rarely used. It's a bit different than CAN. It uses, for lack of a better term, something called a master-slave architecture. The RoboRio acts as a master, and anything connected to the SPI connections is a slave. Normally this is used for sensor networks. Specifically, the one that is used most commonly with the RoboRio is something called the NavX MXP. The NavX includes a gyroscope, which is used for measuring the angular position of the robot, an accelerometer, which measures the acceleration in all 3 directions, forward, back, left, right, up and down. And it also includes a couple of smaller things that are not as important. SPI is used sparingly because if you have a bunch of SPI devices, you also need a bunch of wires that all need to be spliced into the same connections. And it usually makes for a very large rat's nest. I use SPI very, very rarely when I'm communicating between devices because it is very, very fast. But its use is limited in FRC unless you are doing something very specific with very specific sensors. I2C is the next thing that I want to talk about. SPI is up here, by the way, over here. I2C is over here. These 4 pins over here.
I2C is
literally I to C.
Oh.
Like I, the number 2, and then C.
Okay.
It stands for Inter-Integrated Circuit. I2C is another one of those shouty communication profiles, except rather than everybody with CAN just sort of picking their numbers as to what they want to use, everybody with I2C is assigned an address. And that address is specific to you. If you have something specific that you want to do with that address, you reference that number. You don't reference one of 30 different numbers that device might have. But it follows the same paradigm as CAN. You hold up a sign, you shout. If the person wants to talk back, they hold up their sign, and then you guys can start shouting back and forth. And nobody else can talk until the shouting is done. I2C is relatively slow, but works well if you have a lot of similar devices, like the same sensor over and over and over again, that you want to use repeatedly. Let's say that you wanted to put 4 I2C ultrasonic sensors facing in all 4 directions on your robot. That would be a good use of I2C. The only thing about I2C that you have to worry about is the length of your wires. If they get too long, I2C stops working. There's a specific reason for this. It has to do with how resistors and capacitors work and how I2C does its communication at the hardware level. It's not really super important for you to know. What's important for you to know is that if your I2C wires get like 3 or 4 feet long, you're going to start having problems. So short runs is good for I2C.
Like 6 inches or a foot?
You can safely go up to like 2.5 feet and not have a problem with your average gauge of PWM wire. anything longer than that, and you may start noticing that certain data, when it's transmitting really fast, like there's a lot of communications happening on the connection itself, it will come in as gibberish. It will just get all garbled, and that's because the actual process that switches the digital I/O line on and off, it's not turning off fast enough. And so the RoboRio still interprets it as a 1 as opposed to a 0, and that makes a mess. Yes, DJ.
Does the gauge of the wire affect it at all?
The gauge of the wire can. And if we have time at the end and you want to ask why, we can go over that. There is a specific reason as to why it happens. The last thing, which is not used nearly as much because up until very recently, the libraries, at least for Java, for this communication type, were not fully fleshed out. They worked, but not perfectly. Is RS-232 and TTL serial. This is point-to-point. It's designed to let two devices talk to each other without anybody interfering. RS-232 and TTL serial can be fairly fast, depending on what speed you set it to, depending on what your speed requirement actually is. And it is extremely reliable. But you do have the limitation that you only have three RS-232 TTL serial connections on the RoboRio, not including the USB ports, which supposedly work now. I've yet to see it. Supposedly they work. Supposedly you can use the two USB ports that are not the house-style USB port as serial ports in Java now. I've yet to see it work, but they say it works now. Supposedly. But RS-232 is right here. It's the 3-pin connector right underneath I2C and right above DIO. And the two TTLs, which is what you would normally use, are actually on this right here, which is actually what we're going to talk about next. That port, that big long thing in the middle of the RoboRio, is something called the MyRio expansion port, or MXP, is what you'll commonly hear it referred to as. Basically, what it is all the extra inputs and outputs that didn't fit anywhere on these external spots. So they just sort of jammed it in there on its own port. Now, why you would use this, unless you're using a specific expansion board like the NavX MXP, which I mentioned earlier, you probably wouldn't. Because of the shape of the connector, you wouldn't want to connect PWM style cables into it and hope and pray that they stay there. It really doesn't work that way. Normally you would want something to fit into the connector. Now granted, you can do that. It's just you run the risk of wires popping out when your robot bangs around in the field. But normally what you would use it for is someone has designed something to fit into that port to add some accessory functionality to the RoboRio. That's why it's called an expansion port. Probably the most common one you'd see is the NavX, but there are others. There is a expansion board that adds a inbuilt Arduino, another type of microcontroller, similar to the RoboRio, but with much, much less power. It is specifically set up to either drive LEDs, like what you see over on my testing panel, or it has a small TFT LCD screen that you can use to display statistics for your robot, or diagnostic information, or make changes because it is a TFT resistive display, so you can touch it if you wanted to. I haven't seen that used too much, but that's besides the point. And there are a few others. most teams use that port for the NavX. They're using it to add the navigation components of the NavX to their robot so that they can know with relative accuracy where their robot is facing on the field and where it is. The other thing that I'll quickly talk about is the RoboRio inbuilt protection that I talked about earlier. The RoboRio has two types of protection: short fault and cross fault. Short fault means that you've bridged power coming from somewhere directly to ground, which is something that you never want to do with an electronic circuit. But the RoboRio knows well enough that if that is happening, it knows what it looks like and cuts off the power to that particular location. Now, when I say location, I usually mean a certain voltage level. The RoboRio has something called rails. These rails are connections for power. DIO and PWM normally share a rail, although they might be separate now. I can't remember. The USB ports usually have their own rail. There is a 3.3 volt rail, which I have never seen shorted because it's usually not used. But you will know that you have shorted something because the status light, which is directly under the power light, which is right up here in the corner on the RoboRio, will be a very nasty shade of red. And it will sit there, and when you try to enable the robot, it will beep at you. And we'll see it when we look at the driver station a little bit later. There's a little lightning bolt, and you'll see a little blue bar show up and blink on the lightning bolt to tell you that there's a problem. The other thing is cross-fault protection. A cross just means you've swapped two wires. Usually, when the cross-fault connection is triggered, it means that you've swapped power and ground. This is the one that you really want to worry about. The cross-fault protection is not as robust as the short-fault protection because the RoboRio has an extremely difficult time cutting off power that is coming in through a ground. It's very easy for the RoboRio to cut off power that it's providing. It's very difficult for it to cut off power that's being pushed into it. So if you think you have a cross fault, start unplugging as much as you can and start plugging things back in one by one until you produce the fault again, and then immediately shut the robot off once you start having the problem again and go from there. Fix what is broken. One of the last things that I'm going to talk about, which, let me see if I can pull it up real quick. RoboRio imaging tool. See if this is it. Nope. Alright. So, I know where it is. They put it in a really weird spot, but we'll get there. Normally this would be normally this would be a I've forgotten the word. Normally this would be a shortcut on your desktop, but in this case it's not. This is the RoboRio imaging tool. I know you guys are going to have a bit of a hard time seeing it with the fuzzy background. This is what you would use to update the operating system on your RoboRio. It allows you to specify your team number and format the RoboRio, meaning you wipe everything that's on it and put new stuff on it. This is not how you deploy code, mind you, but this is how, when the new operating system updates come out during either the beginning of build season or during build season, you can apply them and make sure that your RoboRio is running the right firmware so that the field technical advisors at the competitions don't come up and yell at you. That's basically what that boils down to. They will make it very, very obvious to you if your firmware is not up to date, because I was a scorekeeper for Pine Tree for a few years, and I can go into a console and see exactly what firmware your robot is running, what firmware your PDP is running, what version of the driver station your computer is running, what operating system your computer is running, I can see just about anything I want. So, at least when it comes to your robot. So, we will know at the field level if you are not running what you are supposed to. And we will make you update before you run a match. And it can be very much a scramble to find the content you need at a competition because normally you will not have Wi-Fi. There are some people that do some tricky things that get them into trouble to get Wi-Fi at competitions, but that's
We'll
besides.
discuss that.
Yeah, yeah.
We're just not gonna do it.
Right. We will not be doing it. All right. So that's my spiel for the Robo Reel. That's the longest part. Does anybody have any questions before I move on?
Does the capacitor with the gauge thing count? Or
No, all the way at the end, TJ.
okay.
All the way at the end. That is more specific to electronics than it is specific to FRC robotics. Oh, hi Hunter.
Is that card that you put on our Robo Rio this year, is that
Yes, that is a NavX.
okay?
That purple thing?
Yeah.
Yeah, that's a NavX.
Did we ever actually use it, or?
No, we never got time to write code for it. So, oops, not what I wanted to do. All right. This is a power distribution panel, PDP. This is where all of the power for your robot comes from. The battery connection comes in right here. Up on these channels here, the big ones, is where you would normally plug bigger motors in, like the sim motors that I was talking about earlier. And down here is where you would normally plug in smaller motors, smaller devices, Bainbot 775s, window motors, stuff like that. When I say that all of your power must come from the PDP, I mean it. If an inspector comes by and sees that you have routed power around the PDP or routed power from somewhere else other than the battery and the PDP, not only will you not be running your robot, but you will also be in trouble. That is a big first no-no because of the protections that the PDP provides. Taking that protection away not only puts your electronic components on your robot at risk, but it also puts you at risk. So first is very, very, very sticklery about making sure that everything that is powered comes from your PDP. Excuse me. Each red and black pair on the PDP is referred to as a channel. There are more than just the channels that you see that the PDP has available to it, but there's only a certain number broken out. The PDP was designed alongside the Robo Rio, and it was determined that this would probably be roughly the number that we would need in order to run a robot. Each channel gets its own breaker, either a 20, a 30, or a 40. In the smaller channels down at the bottom, you either put in a 20 or a 30. They're both the same size. In the bigger ones in the top, you'd put a 40. You cannot put a 20 or a 30 in where a 40 goes, and you can't put a 40 in where a 20 or a 30 would go. They just won't fit. The 40s are probably about 1.25 times bigger than a 20 or a 30. That being said, it will be very, very obvious to you the first time you go to plug in a breaker where it is going to fit. If you try to jam it into one of the slots, it will not work. The next thing that I want to talk really quickly about is battery safety, because it does kind of go hand in hand with the PDP. We did talk about my horror story earlier, where Brady almost arc welded a screwdriver to a battery, but there are some other things to think about. Keep in mind that the batteries that you use for FRC are regular industrial sealed lead acid batteries. They're not anything exceptionally special. You could probably go to Home Depot, Lowe's, Walmart, and pick up essentially the same thing for maybe a little less money and have it work perfectly fine with your robot. But it works the opposite way too. Things that you wouldn't do with a normal battery, you shouldn't be doing with an FRC battery. A couple of things that I always like to mention is do not carry your battery by the leads. I hate it when I see that. I will tell you if I see that, and I will not be happy. I have.
Sorry, I told her already.
um,
I thought that was a,
you thought it was a handle.
yeah.
I have spoken to members of my team about carrying batteries by the leads. It is not something that I like seeing because those leads, while very unlikely, can be ripped out, and it would not be a good day. The other thing is a little bit about what happens if you drop a battery. Dropping a battery from any height is not good. If you set it down on a table a little hard, that's not a big deal. But if you drop it from like more than a couple of inches, there are some things to watch out for. One story that I usually tell when I talk about batteries for FRC is it was a competition probably 4 or 5 years ago now in Boston. A student from another team was carrying a battery at chest height. No big deal. He wasn't carrying it by the leads or anything. And he dropped it on a concrete floor. Batteries are conventionally made up of electrolytes, usually a fluid, and cells, usually metal plates. If the plates break, it changes how the chemical reaction works. And this changed in a fairly fantastical way. A couple of the plates inside the battery broke when it hit the floor. And the battery almost immediately swelled to twice its size.
Oh.
Brad, what'd you do?
It was not me. They ended up having to evacuate the pit for a half an hour. They ended up evacuating, I think, half of the pit. It was a 25 to 50 foot radius that they evacuated, because if the battery had popped, it would have sprayed battery acid, which would have been bad. But the student wasn't doing anything wrong. He was carrying it normally, but accidents do happen. So if you drop a battery, if you see someone drop a battery, make sure to tell someone immediately. I don't care if you dropped it from 6 inches. I don't care if you dropped it from a foot. If you think that you have reasonably dropped it and it looks like it is having some sort of issue, or you've dropped it from an exceptional height, get away and find someone. Running is not recommended. You will get in trouble if you run in the pits.
Very much.
But a brisk walk is acceptable.
Okay.
And that's not to scare you about batteries. It's not meant to terrify you. It's just one of those things where the safety advisors take great care to make sure that there is equipment on site that if a battery should leak or pop, in the case of the battery that was dropped, there is equipment nearby that can be used to deal with it. Some teams do keep stuff on hand for themselves in case a battery leaks. I personally do not agree with that. If there is a problem with one of your FRC batteries, you leave it and you find someone that is an adult or a safety inspector or what have you. You do not deal with it yourself. And that just comes from the fact that I've been burned by battery acid before. It's not fun. It is very difficult to treat. And the people that will have to treat you before the paramedics can get there are going to have very limited resources to deal with it. So it's one of those things where I would rather you get away and leave it there than actually try to have yourself or someone else from your team deal with it. There are people at competitions that are designated to deal with stuff like that. That being said, there is some rarer stuff that does happen with batteries. This past year, a battery did catch fire at a competition. The team had not properly secured their battery. It slid forward in its cage and smashed one of the poles into the battery. This caused a short. The battery got real hot real quick, and the outer casing caught fire. Plastic does burn. So that's fairly rare. The field technical advisor and the field technical advisor's assistant, the FTA and the FTAA, as well as the scorekeeper, have access to a ABCD fire extinguisher. One comes with every field, and it is tested every couple of weeks. So if there is an issue like that, they are the ones that will be dealing with that. The only thing that you guys have to be worried about is if there's a battery fire either in the pit or on the field. The only thing that you guys have to worry about is getting out of Dodge. Do not be in that area, because there will be people running back and forth trying to deal with the issue, and if you're in the way, not only are you going to get yelled at, but you might get shoved out of the way, because a battery fire is about as much of a problem as a battery swelling up. But it's more rare than the expanding battery issue. Batteries expand and contract based on temperature, how much they've been used, stuff like that. As batteries get older, especially FRC batteries, you may actually see the outer casing start to look like it's rippling a little bit. This is because you could almost think of it as like the electrolyte starting to evaporate. It's not really, but as the electrolyte starts to evaporate, it pulls on the sidewalls of the battery and sucks them in a little bit, and you can actually start to see the outlines of the cells in the battery. Not so much of an issue, although it's usually a pretty good indicator that the battery's getting old and you probably won't get too much more life out of it. If it does start to get really bad, if you start to really put it on that battery, like really beat on it, it may stop working altogether, or it may just get warm while you're using it. So something to watch out for, but usually not an issue. The only other thing about batteries that I'll say is when you're working on them, when you're putting leads on, what have you, don't have people touching you. Don't have people messing around you. If your friends are, standing there shoving on you or something, don't. Get out of there or tell them to get out of there. That was part of the reason why Brady's issue happened. He was distracted. There was people around him. He dropped the screwdriver, and luckily enough was able to grab it before it fused to the battery, which would have caused a lot more problems. To quickly finish up with the PDP, there are 3 channels at the very end, at the opposite end of the PDP from where the battery plugs in. These are something called fuse channels. They're a little bit different from breaker channels. Fuse channels are similar to what you have in your average car. At certain current draws, the fuses pop. They essentially burn off the metal that's inside them in order to cut the circuit. So obviously they won't self-reset. You'll have to replace the fuse. But these channels are used for the RoboRio, the pneumatic control module, and the voltage regulator module. It is very, very rare that you would ever burn up a fuse on those. Usually what I see is teams using their pneumatics control module for things other than controlling pneumatics, and that puts too much load on the 20 amp fuse and it ends up burning off. But other than that, I have never seen the RoboRio fuse burn up, and it is rare that the 20 amp one, the one for the VRM and the PCM, to blow up. So, granted, you can still do it, but it's not common. But that being said, to continue with the theme of power, let's talk about the voltage regulator module. The voltage regulator module, which, lovely how that picture is the same size when you click on it as it is when it's on the page. The voltage regulator module is designed for providing power that requires either less voltage, less amperage, or both. Things like your robot radio, which does not require 20 amps to run, does not need to be plugged into one of the big channels on your PDP. This is what that is for. This provides both 12 volt and 5 volt power at different amperages based on what you need to use it for. Most teams just use this to power their robot radio and nothing else. Other teams, depending on what they're doing, may use it to provide additional power for sensors. They may use it to provide additional power to other devices, like an Arduino or another similar microcontroller. And other teams still may use them to power strips of LEDs. Depends on what they are up to. The VRM's not super special. It has two indicator lights on it to indicate whether or not the 12 volt and the 5 volts connections are working. If they are ever off, it means that rail is not working. There is a problem. You've probably burned up your VRM somehow, magically. I don't know how. It'd be very difficult to do that. But maybe it got old, maybe it got dropped, maybe it got stepped on, what have you. And now that's not working. You'll probably have to replace it. The inspectors do check that. I have not seen a specific rule that says if one of your VRM lights is not on, that you cannot pass inspection. But every inspector is a little bit different. Every inspector wishy-washies between how sticklery they are on some things rather than others. So it's always best to have everything working the way it should be. The next thing is the pneumatics control module, or PCM. I don't know why that page is open. Anyways, the pneumatics control module does essentially what the name implies. It controls pneumatic elements on your robot, things that use air. The pneumatic control module is a play on the older style of how we used to control pneumatic devices, which we had little blocks that were like that big that had fuses in them that could control them, or you would drive it off a special module, I guess would be the way to put it, that you actually plugged into the legacy controller, the controller that came before the RoboRio. The pneumatics control module is designed to be fairly robust. It is aware of how much energy it is using, as is the PDP, so it will make an effort to prevent you from doing something ridiculous, but it is not always foolproof. On the PCM, there are several connections. There are two connections over here. There are two sets of connections over here. One is for a pneumatic switch, pneumatic pressure gauge switch, that monitors whether or not your air tanks on your robot are full or not. And the other connection is for powering an onboard compressor. The other 8 sets of connections that are on the rest of the body are for your solenoids. These are the things that direct the air on the robot. The only other connections on the pneumatics control modular, oh my goodness. The only other connections on the pneumatic control module is voltage in, power in from the PDP, and CAN, so you can actually communicate with it to actually give it instructions. One thing that I will mention that is a rule that teams often overlook is what I refer to as the common power rule. When you are running a match, all of your power for that match must come from one battery. Okay? This includes the power that is required to charge your air tanks. So, if you are using pneumatics on your robot, you must use the same battery that you're going to use in the match to charge your air tanks, even if you use an off-board compressor, one that isn't actually on your robot. If you do not, the FTA will walk up to you, say, discharge your air tanks, you have X amount of time to recharge them. Once that time is up, you must get off the field. If you do not complete your recharge in that time, tough. And that's basically what it boils down to. Now, some FTAs are a bit more lenient than others, and they're very, very lenient at off-season competitions. But do not try the patience of the FTA, especially if you meet an FTA named Kate. Kate can be very, very nice, but Kate has a very, very short patience. If you repeatedly do something over and over and over again, the time that you will be allotted to fix it will get shorter and shorter and shorter and shorter until it's non-existent. So be mindful of that. If you are using pneumatics, you have to follow the common power rule. Any energy that is being output by your robot during a match must come from one battery. So, the next thing to talk about is motor controllers. Now, motor controllers come in various shapes and sizes. In this instance, I'm just going to pull up the picture of the Talon SRX because that's one of the more common ones. And there's actually two motor controllers that use this exact form factor. They look almost exactly the same with a couple of exceptions. In fact, on your last year's robot, you guys used Talon SRXs for pretty much everything, if not everything, if I remember correctly.
Did we use a different one?
Yes, we used Victor SPs. They have the same case as this. I'm assuming you recognize what this looks like.
Yeah.
Yeah, it's the same case, it just looks a little bit
It
different.
was just the name that kind of confused me.
Yeah. They look almost identical. So, some basic concepts of motor controllers. Motor controllers are how you control how much energy is going to a particular motor in order to make it turn a certain amount. The way motor controllers accomplish this is a bit cheeky, but it works quite well. Motor controllers essentially switch the input power on and off exceptionally fast, back into that microsecond timing range similar to PWM. There are specific circuits inside the motor controller that do this, and that is why certain types of motor controllers can get very hot. It's because when the switching happens, when the connection is off, all that energy has to go somewhere, and it is normally converted into heat. Talon SRXs, Victor SPs, and some other types of motor controllers have fun tricks that will play with the power a little bit to reduce the amount of heat that is output, and that is why Talon SRXs and Victor SPs don't use fans. Your average motor controller that you would use a couple of years ago, or ones that you might pick up from a hobbyist electronics shop probably would have a small fan or at least a bunch of fins on it. Similar to how the Talon SRX looks, but a little bit more open and probably quite a bit deeper. The Talon SRXs and Victor SPs are exceptionally good at wicking away heat. So you will rarely see an instance where one of them is too hot to touch. I have personally never experienced it, but I have heard of it happening. The other thing that motor controllers do is something called direction reversal. It's basically just feeding power in the opposite way so that the motor turns the opposite direction. All of this sort of comes together into something called the H-bridge format, which is a particular type of motor controller circuit that does essentially what I've described. It looks literally like an H, which is why it's called an H-bridge circuit. But we won't get into that. That's more circuit concepts than basic motor controller concepts. So right here on my screen, I have a Talon SRX. This is probably the best motor controller that you can have. Not so much for how it controls your robot, but how you are capable of controlling your robot with it. Most motor controllers that are available for FRC now behave almost identically in terms of output. You wouldn't notice a difference unless you were really looking for it. With certain older motor controllers, I have developed the ability to feel it, but it is just such a slight difference that your average person who is normal would not feel it. So it's one of those things where it's not really what you buy that you have to worry about. It's what you want it. It's what you want it to be able to do on its own and how you want to talk to it. That's the big things. In the case of the Talon SRX, you can talk to it just about any way that you can imagine. The Talon SRX supports PWM control, CAN control, SPI control, RS-232 serial control, and I believe it also supports pure analog control. I'd have to look. I can't remember.
Brad, how about a break?
Want a break?
Yes.
My mouth is very dry.
Yes. Brad needs a drink.
All right, so we're going to pause for a minute, and we're going to take a break.
What do you think? Like 7 minutes? Be back at 7:30?
Sure.
Yeah. Oh, okay.
Bring again. Gonna miss a part here. We won't try to run over it again. It wasn't that much, but if you have questions, if something feels like it's missing, ask someone to ask me if you don't know me personally, and they'll get you into contact with me. But this right here is your robot radio. It is an OpenMesh OM5P AC dual band router. It is essentially the same thing that you would use to provide yourself internet in your house, just in a smaller package. These access points, these radios, actually run a special operating system, a special firmware that is designed in tandem between OpenMesh and FIRST, because FIRST got into some trouble when they first started using the OpenMesh radios, because they are open source, and you can technically set the gain on the signal so high that you could theoretically interrupt communications for both cordless telephones, other Wi-Fi connections, Bluetooth connections, amongst other things. So FIRST got into some trouble, and they were told to stop using the first version of the radio, and this is what we got, and it has a fixed firmware that you are not allowed to modify, unlike the old one. But that being said, this is how your robot will communicate with your driver station, both on the field and off the field. It can be set up either to communicate directly with the driver station by acting as an access point, something that you would connect to like a normal Wi-Fi network, or it can be set up to only communicate with the field management system, commonly referred to as FMS. Personally, I don't care for the open mesh radios. They have a track record of problems. Antennas coming loose, power connectors coming loose, strange anomalous issues where all of a sudden you can't connect to it and it's not fixed until you update the firmware, even if the firmware doesn't need to be updated. The open mesh radios, in my opinion, were a mistake, and it's an opinion of a lot of people that are like me. But for what we use them for, they hold up fairly well in terms of ruggedization. Now, granted, that still doesn't mean you shouldn't protect your radio. Obviously, if your radio cuts out during a match, you have no communication with your robot will stop moving. Even the automatic functions, even automatic motor functions, will stop happening if your radio gets disconnected from the field while you are running on a match. And this is a safety mechanism. It's called the watchdog. It runs in the background on your RoboRio. It makes sure that it's actually receiving packets from your driver station. And if it's not, it says, everybody stop! And that's basically it. It says everybody stop until it starts communicating again. And if it doesn't ever communicate again, you'll never move again. The only other thing that I'll mention, which I don't have an example of because I don't have it installed on either of these machines, at least not a working install, is something called the FRC Bridge Configuration Utility. There are two versions of it. One is for home use, which allows you to configure it as an access point, so you can connect to your robot wirelessly at home or in your build space. And one is designed specifically for competitions. It communicates directly with the field to pick up on the security keys that you need to communicate with the field with, and will automatically install those keys on your radio so that your robot can communicate correctly with the field. First has done a very good job. A very good job. I went and had a drink of water. I'm not having a stroke. First does a very good job of obfuscating the process by which the radios are set up. There is not a whole lot of work that you have to do in order to make it work. The bridge configuration utility for both scenarios has two text boxes, one button, and the one for home use has two extra check boxes that you'll never use. So for the most part, they make it very, very easy to make interfacing your robot either at home or on the field very, very easy.
So when you say, is it like interacting with the field, does that mean that turns it on to autonomous and turns it off during like a time limit? Or?
Correct. The control packets that are sent from FMS to your robot are specific to your robot, and they contain information about what the robot should be doing generally at any given time. So if it's time to start autonomous, then the field shouts at your robot, autonomous! And your robot takes over from there. If it's time for autonomous to end and teleop to start, field shouts, stop autonomous, start teleop. And that's what it does. The other thing that comes from the field is the control information from your driver station, because your driver station is actually plugged into the field. So it sends something called HID control data, human interface device control data, from your computer over the field to your robot, so that your robot can get the information that it needs from your joysticks and Xbox controllers to actually make your robot do things. And that is where the whole watchdog comes in. Is if those control packets, which is why I call them control packets, aren't heard by the robot, the watchdog says stop, because it is not getting meaningful instruction on what to do next. and first would prefer your robot, which can weigh up to 120 pounds, not go careening into the side of the field. So that's why that's in place.
I got a funny story. I got a
You can still do it as long as there's control packets.
funny story to tell you. The robot always sits straight with the wall.
All right. So, um, we've only got a little bit left to talk about. This next thing that we'll be talking about is specific to the driver's station and the field. I talk about this when I talk about electronics because they're fairly heavily intertwined, and it's a lot easier to talk about this part of it with electronics than it is to talk about it with programming because it just adds more complication to programming. The driver's station is what sends information to your robot, regardless of whether or not you're at home or on the competition field. The driver's station is what takes the inputs from joysticks, Xbox controllers, PlayStation controllers, and converts it into information that can be sent over a network and to your robot for it to be interpreted. From the context of the driver's station, the difference between a joystick, an Xbox controller, and a PlayStation controller is absolutely nothing. Because the way that your driver's station looks at a controller is as a set of axes and buttons. Now, if you actually click on the little icon that looks like the USB symbol on the driver's station, you get this window. Now, normally it would be populated. I don't have any USB HID devices with me, otherwise I'd show you. But right here, you would have a list of USB devices. The ones that are active and plugged in would be green, and the ones that are not would be in gray. And on the right side of this window, you would see a whole array of icons. And when you do stuff with your controller, it will change those icons to tell you what axes are being manipulated. And that's what you use in your code to specify, if I push the joystick forward, the robot goes forward, sort of deal. There are also little indicator lights that if you push a button, they'll light up green and indicate that that is the button that is being pushed. They're in two columns. The first one being index 0, literally button 0, going down to, I think, 13, and then the next column goes down to like 20, I think. I think the maximum number of buttons you can have is something like 20. Now, as I said, this facilitates the communication with your robot. If your robot is not receiving information from the driver station, it will stop. There are several ports that the driver station uses in order to communicate that we won't really get into. But it will be very, very obvious to the people on the field if you have shoved something onto a port that the driver station is trying to use. Because it will show up in your network traffic. Granted, fixing it becomes complicated depending on what you're doing. More often than not, most teams don't run into this because teams aren't creating accessory connections other than the ones that the field provides. You are allowed to, within reason. One thing that I do want to mention, which some of you may be aware of the terminology that I'm about to use, and some of you may not be, that came up at Spirit this year that I've never actually talked about when I've done a training, but I thought I'd mention it. We all know that at times when we're trying to do something on a computer, our antivirus programs can be a major pain in the hindquarters. The driver station does not care for antivirus programs for one specific reason. If your antivirus program also includes a firewall, it can cause problems. The way that the driver station resolves the number that it uses to communicate with your robot is through something called MDNS. It's one of those shouty communication types again. Basically, the driver station shouts a name across the network and says, "What's your number?" Like asking for a phone number from across a room. And if somebody has that name, they'll send their number back. Well, conventionally speaking, firewalls block MDNS because it is fairly easy to manipulate for malicious purposes. So there are specific configurations that you can use in order to save yourself the headache of dealing with MDNS and firewalls. One of the mentors that I was talking to from 58 had been told by a control systems advisor at a competition that MDNS was stupid and that they should be using all static IPs, which means fixing the IPs and then telling the driver station exactly what to look for. Don't do that. Because when somebody else comes by and tries to diagnose why your robot is not communicating with the field, we are not going to be aware that you went into your RoboRio settings and changed everything to be static. And I spent an hour and a half with this poor girl trying to figure out why her robot wouldn't communicate. And it was because MDNS was off. All the connections on the RoboRio had been set to static. I couldn't communicate with it until I finally figured out what the IP address was by flash pinging everything on the network. And finally figured out what it was. And set her all back and shut her firewall off, and that fixed the issue. And they had been running their robots like this for the past 2 or 3 competitions, dealing with communication issues and all kinds of crap because the CSA told them that there was something that was completely wrong. So yeah, if somebody ever tells you to set the IP addresses on your RoboRio to static and then does it for you, find somebody who can change it back. That's not the issue. First moved away from using static IP addresses for everything because teams were having so many problems because people weren't configuring things correctly. And MDNS does an exceptional job at solving that issue. I see the 10. We're almost done. I got a little bit more to talk about. And in fact, it's the last thing. I want to talk a little bit more in depth about FMS, the field management system. FMS has gone through a lot of different iterations, and more recently there have been some mechanisms added to prevent something that I was extremely surprised at seeing in a competition like this. A few years back at a world championship, it was purported that some team members from other teams were using their cell phones to repeatedly send access requests to the field's radio in order to inhibit teams from maintaining their connection with the field. Specific teams. To resolve this issue, first went full network security on FMS. When your robot is communicating with the field, you are on something called a VLAN, a virtual local area connection. None of the other robots are allowed to communicate on those connections. And all other network traffic, with the exception of the network traffic of the field itself, takes the lowest priority compared to your VLAN traffic. So all 6 VLANs for all 6 robots have the same priority. The field's communication has the highest priority, and everybody else has the lowest. This helps to deal with issues where teams will repeatedly spam wireless radios, both the ones on your robot and the one that is connected to the field, to prevent this issue from happening again. While I did not expect it to happen and was a bit dumbfounded to learn that it had happened, I was very happy with FIRST to see that they implemented mechanisms to prevent it in the future, even though they shouldn't have had to. Needless to say, the members of the teams that were caught doing this were barred from the program. So it's not recommended that you try something like it. Yes, Hunter.
Didn't they also have people like activating their hotspots, which is something different robots?
We're going to talk about that in just a second. That's part of FMS. The other thing that was implemented is bandwidth limiting. The field radio is extremely powerful, but it is still just an enterprise router, and that's all it is. It only has a certain amount of throughput that it is capable of reasonably. And when creating connections for 6 different devices to be bridged to it, all sending X amount of data at any given time, it can put a lot of load on the radio. And one thing that was happening was teams were beginning to send 1080p video streams, sometimes multiple, over their network connection on the field. Well, if you get 1 or 2 teams doing that with 1 or 2 cameras, you end up bogging down the field and slowing everybody else down. So your bandwidth on the field is limited. Now, if your bandwidth is excessive, the FTA will tell you to dial it back. And on the dashboard, I normally use a smart dashboard, which is the gray window up here in the corner. But on each dashboard, whether you're using the smart dashboard, the LabVIEW dashboard, what have you, you can control the resolution of your camera and the resolution of the data being transmitted from the dashboards themselves, provided you set it up correctly, which is very difficult to do to set it up incorrectly. But the FTA will let you know if you are using an excessive amount of bandwidth, and will tell you to dial back whatever is using that much bandwidth. Most teams stay well within the range. You won't be running 1080p video at 30 frames, but you could run 1024 by 768 at 15 frames a second, and that would be more than enough for what most teams do. And if you shrink the resolution a little bit to like 640 by 480, you could run at 60 frames, and it would be fine. That being said, I do want to touch very, very quickly on what Hunter had asked. Do not start hotspots at competitions. While in my opinion, it is made out to be more of a big deal than it actually is, because of the type of router that is used in the field, there can be interference had if there are a whole bunch of wireless networks all on the same channels, whether it be a 2.4 gigahertz channel or a 5 gigahertz channel, all in one very small confined area. So first makes the statement and the rule that teams are not allowed to run their own wireless networks while at competitions. This is to prevent that interference with the field. Now, granted, most teams were not doing this maliciously. They were doing it so that they had data to pull down stuff from GitHub or download OS images for the RoboRio or something like that. But this is a no-no. You are still welcome to do USB tethering, which I have done at competitions before, because the frequency for cellular transmissions is significantly different when compared to Wi-Fi. It's well out of the range of interference. You cannot create a wireless hotspot using either Bluetooth or Wi-Fi. Do not use either. You can have them on, do not connect to anything, or do not start a hotspot. You will get in deep trouble if they catch you. You won't be kicked out or anything like that. They'll tell you to turn it off, and they tell you if they catch it again, they're going to talk to one of your mentors. There are some competitions where members of field staff will walk around with a $300 to $1,000 device that can pick up on the exact location where a Wi-Fi network is coming from. They will walk up to you, point their device at you, point at you, and that is your cue to shut it off. If they have to come talk to you, that's a problem. And they are never wrong, these devices. So do not try to make the case that they are wrong. You will be told off. So, that being said, that's everything for electrical that I wanted to talk about. I know TJ has a question that he wants answered that is outside of the scope of this that I will answer after we are off the video. Is there anything specific to this that someone has a quick question about?
So I do have one thing. So just looking and listening, we're gonna have a time where you are actually gonna put hands on.
If you would like a hands-on session to see how things are put together, I do have some snap with me when I get tired. But
I know you're tired, so that's why.
but yes, I mean if we want to sit down and rewire a robot from start to finish, we can.
Okay.
I don't mind that. It's a little Mrs. Klein and I talked about this last time I was here. It's gonna be a little challenging with the holidays, but if we want to do a Saturday or something,
Jason and I have also talked. We've got a few drive trains
We
up.
have some of our dead ones.
We've got the dead ones up there that we'd like to sit down with some of the freshmen and just kind of at leisure.
okay.
Maybe Connor will take it downstairs.
Even if you could hook up the basic controller
Yeah.
with a power supply, like one motor,
Yeah.
so you could
Right.
connect all the pieces to say, this is how you make sure the motor turns. Here's the basic controller input. Like
Right.
nothing fancy, just to see the pieces together. I think.
And
See what you talked about actually.
Yeah, not wire a whole robot.
Right.
I'm thinking like an hour or two.
right, okay. And
Just the basics.
And we can do that. We can discuss a time to do that. Probably, unless we would like to quickly spin through that in the first hour. The next time that we meet, was going to be talking about very general programming.
Are you gonna go towards Java or are you going through C++?
Always Java with new people. C++ can be brain melting
Okay.
for new people.
Because Sky's gonna go right after you and tell you she only wants C++, and Amy's gonna quit if she doesn't have C++. But they come from Texas and that's all they use, so.
I can understand their sentiment as to why they would want to use C++. C++ is significantly more resource efficient than Java is.
Right.
But for teaching it to new people, like I said, it's brain melting.
Okay.
There are some concepts that Java does in the background that you must manage by hand in C++. And if you don't do it right, you have a problem.
So maybe we can talk.
If they would like to talk to me beforehand,
Oh, yeah, no, don't worry, I'll talk to her.
I mean, I can understand their sentiment.
Yeah.
It's just for new people,
No, and that's what we have to deal with right now.
right?
They've been doing it a while, so.
Right.
And
Are they? I assume junior or senior level.
She's senior, she's been doing it for a while. Her brother started the program down in Texas.
Okay.
So they have a lot more experience than these guys do. So we'll start with Java.
Okay.
We'll move into different.
Can you look at your schedule and maybe find a Saturday somewhere?
Yeah.
We don't have to do it right now.